In my first lecture on faunal analysis, I introduced the basics to faunal analysis. In this second lecture, I'd like to talk about gathering primary data and generating secondary data. I'll begin with some basic vocabulary that I didn't give in the first lecture. A taxon is a species, whereas multiple species are taxa. This is another example of Latin words and conjugations used by archaeologists. An element is a single bone. Taxonomy refers to a scheme of classification, and nomenclature is a fancy way of saying names. Proximal is the end of the bone closest to the center of the body. Distal is the end of the bone away from the center of the body. A diaphysis refers to the shaft of a bone, and in plural, diaphyses. Epiphysis is the end of a bone, plural, epiphyses. So one diaphysis has two epiphyses. Articulate refers to fitting together. The primary data collected by faunal analysts is descriptive and we hope replicable. However, it is dependent on sample size and on using consistent recovery methods. The types of primary data usually collected include the elements, including the side, taxonomic identification, the quantification of the specimens, such as count and weight, any butchering or modifications or pathologies on the bones, age and sex, and measurements. An element is a single complete bone, tooth, or shell. If it's complete, you simply call it an element. If it's broken, it's a fragment of an element. There are a few basic steps in identification. First, you need to figure out what kind of bone you have. Is it a long bone? Is it a flat bone? Or an irregular bone? These three different shapes of bones are found across all different types of animal bones, whether it be fish, amphibian, reptile, or mammal, or bird. Do you see any distinguishing morphological characteristics on that bone that would allow you to identify the element? Once you know which bone you have, for example, a tibia, you can look for characteristics that would distinguish that particular species from other species. What if the distinguishing characteristics are missing from your bone? You don't have ridges where muscles attach. You're missing the epiphyses. Well, you would minimally sort to animal class: mammal, fish, reptile, amphibian, or bird. If it's mammal, you can then at least sort to size class. And for your area of the world, there is likely a limited number of species in any one of these size classes. Because most of the bones recovered will be fragmented, and yet information may be gained from how they are fragmented, you want to collect information on which fragments are present. The most basic primary data that you collect is the number of identified specimens per taxon, abbreviated NISP. This is the number of specimens in a sample. Now, if you see two that refit back together, you can count those as one rather than two. However, there are other situations that are less clear and will be dependent upon how your laboratory handles them. How do you deal with specimens with less than 50% remaining? Or how do you deal with jaws that have teeth in them versus loose teeth? Bone modifications that you might record include skinning or butchery marks, cuts, scrapes, chops or hacks, blows, and even saw marks. You might find evidence of cooking or fracture for marrow extraction, as you see in this photograph. You'd want to record any pathologies, such as this fractured and healed goat bone. Determining age and sex. Some main age indicators include tooth eruption, over here on the right, and tooth wear. Of the two, tooth eruption is more precise. However, It can be done only on young animals, up to the point at which all of their teeth are erupted. Tooth wear is somewhat dependent on diet, and therefore not quite as precise as tooth eruption. Another age indicator is epiphyseal closure. When mammals are young, the epiphyses are not connected to the diaphysis. In between the two are growth plates, which is how the bone gets larger and therefore the mammal gets larger. On the right, you see an unfused young juvenile roe deer, humerus. On the left, an adult roe deer. All those separate pieces are now fused together and growth has stopped. So you would record for each epiphysis, which the distal epiphysis might fuse at a different rate than the proximal epiphysis. Is it unfused? Is it partially fused? Or is it totally fused? Annular rings may also show age, and not only age, but season of death. So for example, on the left, you see a clam with annual light and dark shell increments. On the right, a fish ear bone, known as an otolith. Sexually diagnostic features are uncommon. One might be antlers still attached to a skull. Another might be spurs on a bird's leg. Medullary bone is found seasonally only in female birds. And of course, measurements need to be taken. And the illustration on the left kind of hints at some of the different types of measurements that you might take. Now that you've collected your primary data, how can you take that a step further using secondary data? What you can interpret is highly dependent on sample size. This cannot be emphasized enough. You must meet the test of adequacy to be able to compare your assemblage with other assemblages. That is, your assemblage must have over 200 individuals, or at least 1,400 total bones. Number of identified specimens per taxon, in and of itself, is not a very useful measure. To use it by itself, we would have to assume that all elements and all taxa are equally identifiable. We would have to assume that recovery rates are constant for each taxon and element. And of course, we know that we are biased for finding larger bones and not finding the smaller bones. And that cultural and non-cultural breakage are uniform. And of course, we know that different bones have different densities and therefore would break at different rates. However, you may show an anatomical distribution of the number of identified specimens graphically. I like this type of illustration. The darker shows more than 10%, and the lightest stippling shows less than 3%, and the uncolored bones were not found. You may also illustrate it by element. I find this graph a lot less useful myself. However, I like this graph where you illustrate it by anatomical region. One common measurement that faunal analysts figure is the minimum number of individuals per taxon, or MNI. To derive this, you count the most common single element in a species. However, to be accurate, you must also consider the age, the sex, the size of the animal, and the portion of bone. Figuring this will allow you to say the minimum number. So for example, there must have been at least 46 deer in this assemblage, at least 24 turtles, at least 14 freshwater fishes. So the phrase that you need to say to yourself is, there must have been at least how many? Let's take this example where we have a cow, and here's the list of bones that were recovered, a dog or a wolf, here's the list of bones that were recovered, and a rabbit. What was the NISP for the rabbit? Well, we only found one bone, therefore we have only one element, the number is 1. How many were for the wolf? Well, we found 3 bones, the number would be 3. And for the cow, we found, let's see, 3 molars plus 6 ribs, that's 9, plus 3 more bones, 12. However, what would be the minimum number of individuals? There must have been at least how many rabbits? There must have been at least how many wolves? There must have been at least how many cows? Well, let's see, only 1 bone for the rabbit, so there must have been at least 1 rabbit. Well, the highest number we have for the wolf is 1 of each. And how about the cow? The MNI for each of these is 1. I'll give you another example. What is the minimum number of individuals it would have taken to produce this assemblage? Now, some of these elements are found on both sides of the body. So metatarsals are found on the right side, on the left side, front and back. Femurs are found on the left side, the front side, front and back. But some are, there's only one, or they're not bilateral, skulls and vertebra. And of course, ribs here are not specified as to which rib. So what's the minimum number of individuals that you think it would have taken to create this assemblage? There must have been at least 22 deer, because you have 22 right rear metatarsals. Each deer has only 1 of those. There must have been at least 22 deer. Now let's complicate this a little bit more. And if we knew the ages or age ranges, now with this more information, what's the minimum number of individuals? We'd look first here at adults, and all 8 rib fragments are adult. We have 5 adult right rear metatarsals. Look at this. There must have been at least 16 adults, because there are 16 C1 vertebrae. Each animal has only 1 C1 vertebra. Among the juvenile, there must have been at least 17 juveniles. And among the infants, there must have been at least 3. That's a total of at least 36 deer. Another measure is to estimate the biomass, or edible meat weight. You multiply minimum number of individuals times the pounds of edible meat per taxon. You need to include the age and sex in your considerations. This derived biomass can result in wide errors, and therefore you must specify the math formulas that you used. So for example, an adult deer in South Carolina weighs a lot less than an adult deer, say, up in Iowa. A male deer might weigh more than a female deer. A young deer will weigh less. Another consideration is what is considered edible meat. What we today consider to be edible meat may or may not be what people in the past considered to be edible meat. So you can see where there are a number of problems with figuring this derived number. Let's look, for example, at the minimum number of individuals. 50 squirrels. They sound pretty important. Only 2 deer. But if you think about that in terms of edible meat weight or biomass, which one of these was more important? Squirrels or deer? Well, I have to say that I think 2 deer have more meat than 50 squirrels. Here's an example showing number of unidentified specimens, minimum number of individuals, and biomass. If you look at the number of identified specimens, we have mostly shark, rays, and fishes, 38.2%. Secondarily, edible mollusks. And after that, commensal invertebrates. And after that, domestic animals, mammals. If you look at the minimum number of individuals, the numbers are a little bit different. Mostly edible mollusks, then commensal invertebrates, then sharks and rays and fishes. But if you look at biomass, what percentage of these contributed to the diet? By far the most important item in the diet was domestic mammals, and following that, wild terrestrial mammals, and way far down, sharks, rays, and fishes. Body part quantification can be important in studies of taphonomic factors, butchering, transport, food preparation, disposal habits, nutritional analysis, and foodways, such as issues of status or ethnic differences or social setting. Who gets the fine cuts of meat? Who gets the foot bones to make soup out of? You could base your body part quantification on skeletal elements, such as the femur or the humerus or a metatarsal, or on anatomical regions, such as a forelimb or feet, or butchering units, such as flank steak. You can group these as high value, medium value, or low value meats. And of course, we're basing that somewhat on our modern day, what we consider to be high value, medium value, or low value. One way to analyze the use or the choices of high utility versus medium or low utility is to compare your assemblage to that of a modern day deer. If you look at a modern day deer, by far most of the elements are of low value, low food value. Next most common are medium value, and very relatively few are high value food items. You look at these two different assemblages from the Kincaid site, by far most of what people have brought back to town are medium value food items, and secondarily high value, and very few of the low value. Another way to illustrate the comparison is to have a line coming up the center here that represents the deer skeleton, or the deer, and anything on this side of the line has more than would be found in a deer, and anything on this side is showing less than. So we're finding more upper forelimbs and upper hind limbs than would happen if you were just randomly bringing back bones from a deer, and fewer lower limb bones, feet, skull, and axial elements. You can measure diversity. You can calculate diversity versus equitability to explore resource use in terms of niche breadth. There are a number of statistical methods you can take to look at this, but basically you're looking at how many species were used and how much each was relied upon. Knowing this can tell you whether the society practiced a focal economy or a diffuse economy. In a focal economy, the society depends on just a few species, although they may continue to eat a variety of foods. Whereas in a diffuse economy, a society eats many different species without emphasizing any one of them. I made this bar chart. Which color do you think represents a focal economy? Both of these societies are eating 8 different animal meats. Sure enough, the blue are depending on just 3 and not eating many of the other 5, whereas the green bars represent somebody with the diffuse economy, not emphasizing any one type of meat over another. To summarize, zooarchaeologist collects primary descriptive data, such as bone identification, number of specimens by taxon, quantities, age, sex, modifications, pathologies, and size. Sample size is very important. To be comparative, your sample needs to meet the test of adequacy. Over 200 individuals, or at least 1,400 total bones. The zooarchaeologist interprets the primary data and often presents secondary data, such as the minimum number of individuals, the biomass, the body part quantification, and assessment of diet breadth or diversity. If you'd like to learn more about what types of interpretations are given by the zooarchaeologist or faunal analyst, please watch the 3rd presentation in this series on faunal analysis.